a look at the time series of global surface temperature, water vapor, and the precipitation during the past 3 decades. We focus on this period because we only got a global coverage data set for this period. So this figure shows the time series over the global ocean. Left panel is the global ocean. Right one is for the tropical mean. The upper one is for the SST mean. The middle one is for the column water vapor. It's integrated troposphere water vapor. The lower time series shows the precipitation. We can see for the SST change during this period, there is the SST keep warming for the global ocean and also in the tropical ocean. But in the tropical, there are also some very strong interannual change corresponding to the El Nino events. Water vapor is generally follow the surface temperature. We can see the water vapor is also the increase during this time period. And the water vapor data record is only after 1987 for the Saturn night observation. For the precipitation, we can see the increase is not very clear. It's basically muted. So, but at the same time, we can see there's very strong fluctuation is corresponding to the ENSO events. And this is for the over ocean. This is ocean and land together. We can see for the surface temperature is keep increasing during the past 3 decades. And this is in the tropical region. For the precipitation at the same, we can see the increase or the change is very weak in the globally. But in the tropical, we can find some increase, but it's weak. This is over land. Over land, we can see the surface temperature is the increase is even stronger in the global land and the tropical land. And this is for the precipitation in the tropical mean and the global mean. So the basic message here is interdecadal and the long-term change during this period exist in the surface temperature and the troposphere water vapor. However, the long-term precipitation change in general weak, but with strong interannual variation, even for the tropical oceanic precipitation. At the same time, we can see for example, we take a look at the global mean SST. We can see it seems there's 2 periods. After 97, 98 big El Nino events, the surface temperature SST is become flat. It's not keep increasing. So it seems there's 2 distinct periods before these events. So especially over the ocean. We go further to calculate the change rate of precipitation and the troposphere water vapor. We want to see how big changes in the precipitation and the water vapor with surface temperature change during this period. And these 3 columns shows the global ocean, land and the ocean together. And this one is for the water vapor change. This is the precipitation percentage change with surface temperature. We calculated the linear change for the water vapor and the precipitation for different regions. And at the same time, we calculated the linear change for the surface temperature during the same region and the same period. So for the global oceanic mean, we can see the water vapor is increase is about 8%. But for the surface precipitation, the change is very weak. It could be positive or negative. In the tropical region, we can see the water vapor increase is over 10%. But for the precipitation increase, suppose that in the tropical region, the precipitation should must be increased with surface temperature But the magnitude of increase is still much smaller than the water vapor in the tropical region. We go further to take a look at the global map of linear change for these three variables. The upper one is for the surface temperature change. The middle one is for the oceanic column water vapor. The lower one is for the precipitation. We separate it into two periods because the SSMI the water vapor data is only available for this period. So we calculate the linear change at each grid point. We can see the spatial structure is very complicated, even for the surface temperature. But for the surface temperature, we can see the largest increase is in the north hemisphere higher latitude. And also, the surface warming during this period is not spatially homogeneous. We can see that especially in the tropical Pacific, in the east basin actually is a decrease during this period. At the same time, we take a look at the water vapor. The water vapor is, we can see there is a big band. It's increase along the, roughly along the ITCZ, and also there is a decrease the north or south of this band. At another basin, we can see the water vapor is basically the increase. For the precipitation, the structure, the spatial structure is roughly corresponding to the water vapor structure. There is an increased band in the deep tropics, and also there is the decrease, the reduction at the north or south way. Another basin we can see there is in the tropical basin, in the Indian Ocean is increase. It's Atlantic Ocean is also increase. But higher latitude there's some signals. So the question is, what is the reason to shape this kind of spatial structure during the past 3 decades? We try to find some reasons behind of this spatial feature, and also we wanted to find some why the changes, as I showed before the time series, why even the surface temperature change after 97, 98 El Nino is become weaker. So the two candidates is global surface warming and also the PDV. And based on this surface temperature map, this is a linear trend at each grid point. We can see this pattern tends to similar to the PDV, the classical PDV pattern. Then I try to introduce some information about the data set. The major data set we use is the GPCP monthly data. It's version 2.2. This is basic resources for this data set. It includes the infrared-based rain rate estimate, and also after 1987 we have a microwave-based rain rate estimate. Overland we have rain gauge data. Currently the data set is covered this time period is basically cover 1979 to the present, over 30 years. And also the spatial record is 2.5 degree. Other satellite and station-based product is we use NASA gauge surface temperature anomaly. At the same time, we use non-recorded SST from NSEP ERS version 3. For the water vapor, we have SSMI and SSMI-S. We merged this product from different sensors. We use the RSS retrievals. So it's roughly covered 1988 to 2010. So basically, we focus on this period because we have surface temperature data, and also we have water vapor data over this period. As I just said, the spatial structure of the linear change during past 3 decades is very complicated, especially in the deep tropics. So there are 2 candidates to explain this kind of structure and the change. The first thing we wanted to know, what is if there is no PDV change during the past 3 decades, what does it look like? The reason is only from global mean surface warming. What does it look like for the SST and water vapor and especially for the precipitation. So we choose a global mean surface temperature anomaly as the index to do the regression. And we focus on this period. We have the water vapor data, and also we do for the entire record, GPCP record. So this is the regression map from SST. The striking feature is that there is a warming along the equator in the deep tropics, especially in the tropical Pacific. At the same time, we can see the water vapor is also increasing in the deep tropics along the equator. And for the precipitation, also we can see that there is a big increase in this especially covers the entire deep tropics in the Pacific Ocean. And for this two period, the spatial structure is basically is very similar. So we compare this global mean surface warming related to the change compared to the observed change during this time period. And this observed change, as I just showed, is just a linear change at each grid point. So this is the surface temperature. This is we claim is global mean surface temperature warming related to change. Compare these two, there's a big difference, especially in the deep tropics in the Pacific Ocean. Observed linear change is kind of similar to the PDV pattern. It's a cooling in the east and the central Pacific. But related to the global surface warming is a big increase in the deep tropics. And this is for the water vapor. The water vapor is also, we can see the big difference for the spatial structure. For the precipitation is also, the big difference is in the Pacific Ocean. This is positive corresponding to the narrow band of increase, and but there is a big decrease in the north and south of this band. So the conclusion is global mean surface warming cannot explain observed change during the past 3 decades, especially in the Pacific Basin. There should be another reason. So we go back to this time series. This is global mean surface temperature, SST. This is for the tropical mean. We can see there is, as I just said, there is simply there is two mean climate state. Right before this big El Nino events, and this is water vapor and the precipitation. So there is the same as there is a climate shift around this time, or to get an index for the PDV signal in the Pacific Basin. So we have to use a longer record of SST, global SST. So here actually we use the NSF ERSST. We choose a time period is from 1949 to the present. We do the UF analysis for this Pacific Basin is 60 to 60, and we got 4 major modes. The first one we can see the high frequency is basically corresponding to the ENSO signal, but at the same time we can see there is a shift around the 76 and 77 is here. There is 2 period. So it means the first mode is got the 2 things. One is the ENSO events. Another one is this climate shift around the 1970s. The second mode is basically dominated by the shift in the 98 and 99. We can see there's a big jump around this time period. The third and the fourth is basically corresponding to the ENSO. We can directly compare with the global mean surface anomaly, this time series. we can see the first one actually is very similar to this time series, and we can see the 76 and the 77 shift, and also we can got some signal is around here about this shift, and this is compared. This is the PC for the principal components for the global SST anomaly, and the second mode for the global SST is also very similar to the PC2 from the Pacific Basin. So this is tends to confirm that the PDV change is in the global SST, and also so we further to do some simple confirmation to use the global SST. We just simply separated the period we forecast is from 79 to 2010 into 3 periods, because we found that the climate shift is around 97, 98. So we separated this global SST into 2 major periods. The first is the recent period, is after 97, and also there's the early period is we wanted to see whether this PDV shift is in the SST or not, and this is we divided this period into 2 sub periods. We wanted to check whether there is some whether the PDV signal is consistent or not. So we take the difference for this 3 period. The first is later period minus the early period. We can see this pattern is very similar to the PDV related SST change. The 2 sub period shows the same quantitatively same spatial pattern, but for the early period with these 2 sub period, there is no PDV signal. Actually, the signal is dominated by the ENSO signal in the deep tropics. So this kind of confirms that the PDV signal is in the global SST field. As I just said, the first principal components and the fourth components is related to the ENSO. This is a regression map. So for the first, this is SST, this is water vapor, this is precipitation. So we can see this pattern is typically El Nino pattern. And the second one is basically, we can see the center is in the Central Pacific. So it's basically corresponding to the Central Pacific warming events. For the PC2, we wanted to is this principal component is related to the PDV shift, and this is for the entire record. We actually focus on the later period after 88. We can we do the regression to this time, the red one. We got this spatial structure. This is SST, this is water vapor, this is precipitation. We can see the SST is basically very similar to the classic PDV pattern. We compare this pattern to the global mean surface warming related to the structure, and this is related to the PDV, and this is related to the global mean surface warming. We can see the big difference exists in the deep tropics. For the PDV, is basically warming in the Central and East Pacific, but for the global warming related to the change is increase along the deep tropics, and for the water vapor, also we can find the big difference in the deep tropics. This is for the precipitation. So the basic conclusion is the spatial structure are totally different from between associated with global mean surface warming and PDV related to the change. But also we can see during the other basin, we take a look at the SST. We can see during the others, for example, in the Indian Ocean and the Atlantic Ocean, the structure is basically is very similar. And for the precipitation, we can find the very similar features for these two reasons. We compare these two to the we call it the observed change, and also is a linear fate at each grid point. We can see this linear change tends to be the combination of these two factors. We do the simple exercise. This is the surface warming related to the change. This is the PDV related to the change. We just choose the 60% of surface warming change and 100% the PDV change. We got a combination of this pattern, and this is for the SST. This is for the water vapor. This is for the precipitation. We compare this this is a combination of these two factors, and this is observed change. We compare these two; they are very similar, and this is for the SST change, and this is for the water vapor change. This is for the precipitation change. Especially in the deep tropics, we can see the precipitation change structure is very similar between the observed change, and this is a kind of artificial combination of these two factors. So it seems that observed change during the past 3 decades is these two factors. One is global warming, and also another one is PDV change. So the summary is the first summary is the first conclusion is the global mean surface SST, global mean SST, land surface temperature, and the troposphere water vapor is keep increase during this time period. However, the changes in the global mean precipitation is in general weak. But we can see there is a tropical precipitation actually increase during this period. Global mean surface and land warming, surface warming and land surface warming is linked to the precipitation and the water vapor anomaly pattern. It's different from what we have observed during the past 3 decades, especially in the tropical Pacific basin. So this means there should be other factors that play a role. The UF analysis used the relative long record SST anomaly. We found that there exists a climate shift around this time period, and based on the spatial pattern, and this shift is related to the Pacific decadal variability. So the major conclusion is observe the long-term and interdecadal change, especially in the precipitation and the troposphere water vapor during this time period, is a combination of global surface warming and the PDV. This kind of a special pattern is a band of increase along the equator in these two variables, especially in the tropical Central and East Pacific, and with 2 reduction south and north of it, and this is caused by the opposite effect from the global mean surface warming and the PDV related to the change. PDV change during this period in the East Pacific is basically a cooling, is kind of like a La Nina cooling. And also the point is this observed, we can see there is a narrow band of precipitation increase in the Central and the East Pacific. So this could be evidence for the influence of global mean surface warming in the deep tropics. Thanks. PDV is,
first of all, is it the same thing that sometimes is called PDO?
I think it's the same. So it's just used different. Yeah, PDV is in the deep tropics. The signal is kind of like El Nino, but over a broader region, and also the oscillation period the period is longer than the El Nino. The major center is actually is in the subtropics. It's not in the deep tropics.
So the way you put this was that it's as if it's a forcing. But is it what's forcing for PDO and PDV? Or is it simply an internal oscillation? And is it
I think PDV is an internal oscillation. It's not it's oceanic system. So here we just take a PDV as a forcing to the atmosphere system. So precipitation is just as a response to the PDV forcing. So we don't know what the reason caused the PDV.
Is it true that, a lot of other research has indicated that the shift in 76, 77, and also the shift in 98 was related to that?
Yeah, based on the spatial pattern, they are very similar, but on different phase.
Right.
Yeah.
But the long-term shift he showed when we going back even to the 50s.
Mm-hmm.
That shift is related mainly to the PDO, PDV. We haven't done that. Other people
I've heard this, yeah.
Yes, this is a.
And it's an internal oscillation, a long-term, interdecadal kind of overturning, and mainly in the Pacific Ocean, which drives the whole thing. And it's kind of interesting in some of the diagrams Guojun showed, you could see a lot of similarities, like in the Indian Ocean and the Atlantic Ocean, of the long term in the PDO, but it was the Pacific that was different. So the question is, in terms of the precipitation patterns, the PDO, PDV is very dominant, but there's also this overlaying this is this global warming. And maybe you can go back to a couple of near the end there where you have those different.
Uses a special pattern, I think.
If you go back to just go back to one there, the one you just had.
Mm-hmm.
The way he's done this is the changes related to the PDV shift are on the left-hand side. He's tried to separate those out. And the changes due to the global mean surface temperature warming, and they're radically different. But if you look closely, they're not radically different except in the Pacific. Like if you look at the two SST patterns, the Atlantic looks like the Atlantic in both of them, and the Indian Ocean. And if you look in the water vapor, you see a similar type of thing where it's just the Pacific being different. And even in the precipitation, the pattern in the Indian Ocean and the pattern in the Atlantic is similar. And the Pacific is really different. So I think one of the things that Guojun's analysis indicates that, first of all, that these things are different, and that when you look at the actual precipitation change pattern, you're getting a mixture of these two things. And so one of the interesting questions, like if you're comparing to climate models, climate projections of what the precipitation pattern change would look like, you can look at, if he's basically separated these two. So if you can get to the, let's see, the changes related to the global warming pattern, you have a comparison of like the right-hand strip here and the observations.
Yes, this one I think.
It's in there somewhere.
Yeah, it's here.
So
This is
here,
observed.
Here the observed bits on the left. And here are the estimates of what the PDV effect is and what the effect of the mean surface warming. And so you can go back and forth again, the Indian and Atlantic, it looks like what you get from mean global warming. But when you look in the Pacific, you have this mixture. But essentially the right-hand column is showing you what the patterns would be if it was just global warming. So it's an estimate of just the global warming precipitation change. And I think, so if you're going to use a climate, for example, the bottom right-hand panel, you're going to look at what a climate model showed you during that period. this is what you ought to see in terms of a precipitation pattern for just global warming.
That's based on the regression between the temperature and the
Right.
precipitation.
Right.
So it's sort of a projected estimate based on a correlation between increases in surface temperature and precipitation.
Exactly. I mean, this is, not proven, obviously, but it's
Okay, but that's your
it's
estimate. Yeah.
trying to pull out. You only got 30 years of information here, but the fact that we can sort of reproduce SST, water vapor, and precipitation, and some of these different patterns, and add these up in the same way, I think reinforces the idea that this might be a valid approach.
How did you come to the weights of 60 and 100?
That's arbitrary.
Just
That's
arbitrary.
arbitrary.
Yeah, we assume that the singular from
50 and 90 or something.
you can tune it.
Get out of the analysis,
Yeah.
but it'll be interesting to see what the reviewers say.
Thank you.
Okay.
Okay. Back to questions rather than discussion section. One of your points is that global precipitation is stable. At least it's against my expectation that should increase within reason SST. What mechanisms are behind this stability of precipitation?
Yeah, I didn't really get your question. Is why the global mean precipitation is weak? Okay. Yeah. Actually, there's some results shows that the modern results shows that global precipitation must be weaker than the water vapor increase. Yeah, the major argument is based on the energy balance. For example, the water vapor increase is basically for the surface temperature change and also the atmosphere holding capacity. But the precipitation change actually is determined by the entire troposphere energy budget. So SST change, surface warming, does not mean the troposphere cooling will increase. It's a totally different mechanism.
I try to understand the scale between the PDV
Mm-hmm.
and the US surface warming. My question would be this. Of course, you're using 30 years data here. Seems to me, the PDV inertial variation plays major part, I'm not sure, you correct me, the major important contribution. And the surface warming somehow modified. But I'm not sure, say, if you say you're only using 10 years or 20 years, will you still be able to see this kind of correlation? I'm sorry, my question is simple. The PDV and the mean surface warming time scale, the impact.
Yeah, probably it should be opposite. I think it's
I'm sorry, okay. So
yeah, it's PDV. It's modulate the surface. It's long-term surface change. The PDV just gives some impact in the certain period. It's not continuous for the entire time period.
All right, so basically their time scale is comparable, those two factors.
And it depends. It depends. I think if you define a global surface warming, the global surface warming should be dependent on the carbon dioxide is related to the surface warming. It's long-term, but the PDV is a decadal change, so it's several decades. So there is an oscillation. It's a positive and negative. So it should be shorter than this kind of force.
And then you, Bob.
I have a comment related to the previous question or comment. It seems that your analysis clearly shows that the column water vapor is increasing
Yes.
at a much higher rate than the precipitation.
Yeah.
So it means that the atmosphere is getting moister. You're storing more water vapor in the atmosphere. Right?
Yeah.
Because you just look at the water balance equation,
Mm-hmm.
that becomes the so-called storage term, which at least globally, if not regionally, is typically assumed that there is no storage. So now we're seeing storage in the atmosphere. And I wonder what the impact of that would be on as a feedback mechanism for global warming, because water vapor is a very potent greenhouse gas.
Uh-huh.
And I wonder if that might enhance the warming effects and have kind of a positive feedback. Have you looked into that at all?
Yeah, I think it's hard. I think the major issue is data record is too short. It's about try.
It's too short.
Yeah,
Puts
it's
everything into doubt then what you're doing.
yeah, it's regarding the feedback. I think it's hard to assess. It's
Well, wait a minute, hold on. I mean, it's not that there's no storage, Arnie. I mean, there's always been storage, but there's always been water vapor.
Yeah, but it's not precipitate, it's for storage.
There's
relative
humidity can be. I mean, there's sort of a 9-day residence time, right? Turnover time for water vapor in the atmosphere. There's a tiny bit of storage, always has been. The water vapor,
What's happening with this increase in common water vapor?
the models have always predicted since they started that water vapor, that relative humidity near the surface is going to stay constant.
Mhm.
So water vapor goes up roughly 7% per degree of warming to the surface.
Mm-hmm.
And until recently, the odds were not very good, but now they're better, and they do indicate that there seems to be an approximately 7% increase per degree warming. And we have, in the last 30 years or 25 years, about a half a degree of warming and a corresponding amount of water vapor increase. The argument that was referred to about the precip is a model-based argument. Well, it's theoretical, but it's confirmed by the models, which is that the real constraint on total precip is how much condensation heating is possible.
Yeah.
Because you got to radiate that heating. It's got to
Right.
balance with the temperature. So the models tend to cluster around 2% per degree. The data shows a little less than that. And we've looked at data for the whole 20th century, shows about 1% per degree, roughly. The more recent
1%
period,
increase in precipitation.
yeah, the more recent period shows less than that,
Mhm.
but still maybe positive if you allow for, the error bars are big enough to include zero. So that one's still kind of an open question. As is this constant relative humidity business, because that is still
Right.
more strongly seen in the models than it is in the data. The data are still a little bit
What, in terms of constant relative?
Yeah, I mean, it would be nice to have better data for that.
And I think because the really good data is only about 20,
Yeah, 24
25 years.
Yeah. Good data in terms of.
Well, almost everything. You get SST goes back further, but in terms of water vapor and precipitation, you can't really go back that far. And I think one of the things is, like for example, the GPCP precipitation global record is just about flat.
Right.
Okay?
Yeah,
And like Phil said, I mean that's probably within the error bar 2%. It could be 2%. But one of the things is it also is possible. We haven't really got to this, but you have some interdecadal things like the PDO, PDV that obviously has got strong signals.
absolutely, yes.
And so if we can figure out a way to sort of integrate that and try to take that out, because what might surprise people coming up here is if you go into another climate regime on the interdecadal scale, all of a sudden your precipitation could start increasing with time. And, and even the patterns would change. But at the moment, I think we've got a little bit of a handle on the patterns. One of the interesting things I find on these slides, though, is the patterns and the change and how everything we're adding up together here is almost all ocean stuff. And the pattern of change over land is relatively weak, and I'm not too sure how much of a difference there is. And of course, that to a large degree, that's what everybody's interested in. How's the precipitation over land going
Yeah.
to change?
Yeah, hour by hour.
Right, yeah, I know.
Kilometer by kilometer.
Right,
What,
yeah.
did you see the science paper about salinity changes?
Yes, the recent one.
ISP?
Mhm.
So I was at a meeting last week where Dirac was there, and we talked about this stuff, and there's 2 points where, so for people that didn't see it, it's they talked about the large changes in E minus P pattern over the past 50 years, 60 years, and corresponding changes in sea surface salinity. And they interpret this, they sort of headline it as dramatic, very large changes in the hydrological cycle. They compare it to the models, and so it turns out that it's not a globally integrated change, which is the only number that I think makes sense. So I don't know what it quite means, but they do show really large changes in the pattern
do
Do
they
you have an answer?
have they used a longer record of salinity data? I don't remember.
1950 to the present.
Yeah, I remember there is a longer record.
The other issue there is that until about 2003 or 4,
Mm-hmm.
everything's based on a really sparse network, and then all of a sudden they get this huge increase
And also,
in
when I
data.
read the article, it seemed to me the whole thing was based on, they did some adjustment of the early part. They have an absolute magnitude problem, and they had to do some adjustment. And that adjustment seemed to be about as big as their signal.
There were two salinity people there. Who, one of them showed me a plot that shows that they have this trend,
Mm-hmm.
but the data are they've got 99% of the data points at one end of the trend, and everything else scattered out around the rest.
I mean, I don't know if you felt that way. I read that paper, and I basically said, reject. You know, I said their data, I mean, the conclusion is really interesting and everything, but the data doesn't, you know, the adjustment they had to do.
Well, did you read the earlier? I mean, better to read the earlier paper, which was more complete.
Okay.
Actually, unless it's related to what you're discussing right now, I'd like to ask this question. He's been waiting 10 minutes.
The substance temperature indicator for the global warming, that's done a lot of work on that. But how to calculate the surface temperature? I noticed that you have the ocean global temperature and also tropical temperature.
Mm-hmm.
How do you calculate that?
You mean the time series?
Well, you have the value for each time, right?
Yes.
At the very beginning.
Yeah.
So for each time, you calculate the one temperature represents the global temperature.
Yeah, we just
tropical temperature.
yeah we just
How do you
average
calculate
the entire domain. Use the
average
air weight.
the global
Yeah,
temperature?
air weight average for each month. We got a number for each month.
Yeah, I mean, how to calculate the temperature, the way you mentioned, or some people use the other way. I think that might be kind of impact to your final results, because when you see those kind of changes, particularly for the variable not that significant or easy to pick up,
Uh-huh.
then calculate the temperature, the way that you use it might be very important, particularly probably for the length of the temperature, you included that. The length of the temperature variation is big, and even for the ocean temperature, it's relatively stable, but for length of the temperature, changes is very big. So when you do the calculation for the mean or for the tropical area, say,
Mm-hmm.
then the spatial average, how you do that,
Yeah,
it's very important.
yeah we take the because the for each grade, I mean in the higher latitude, the error is small, so you should take the error weight average, to times about the cosine theta for each grade point, and then take the average of the box.
Well,
I mean, we're just
The box are
using-
different.
We don't calculate the temperatures themselves. I mean, we're using data sets provided by other people.
It's graded data.
NIST and NOAA, and all we're doing is area averaging.
Yeah.
yeah, okay, so if you do the area average, for the ocean area, it might be okay, but I'm talking about the tropical average.
Uh-huh.
And for the ocean temperature, it's okay because the variation within space is not that much. But if when you do the average for the tropical area, say,
Mhm.
the land, then the land temperature for a small scale or spatial scale, the variation may be very big. So when you do the average, how big the area is will be the impact.
What we use is the graded data, so it's the data is at each grade point.
You read the data,
Yeah.
You use the tropical area.
Uh-huh.
So you within 1 degree, 5 degree,
Uh,
or 10 degree?
here is about 1 degree data.
How many?
1 degree data.
1 degree.
Yeah.
1 degree grid.
Around
1
the
degree
tropical,
grade. So
around the tropical, right?
yeah.
This is the minimum of the graded data.
Yeah, there's some data is 0.5. I think from case data, they provide 0.5 degree.
I think in terms of climatology data, probably not make that difference or authority data. I personally also produce those. Actually, I try to, but I think running time is running short, but I'm not going to stop that. But perhaps for this kind of starting quarter degree and 1 degree may not have too much impact. That's my own personal experience, but I'm not sure about
That's what I said, that for the ocean surface it's okay, but for the land.
But yes, but even so.
This is a question.
And sir, did you have a question?
No, I just try to Bob about this latent heat. So the EMS.
Okay.
I just want to know what the EEPROC, the data EEPROC they use the data.
Okay, my question is,
Well,
there
you
is so many things happening in 1998. If I remember, MCA being from 1998, do you think it's maybe restricted because the saline change or the MCA being from 1998?
Absolutely, but the question is we use that. Yeah, we use a different data set. Actually, the water vapor data is also shows there's a shift. The water vapor data is truly SSMI.
It's just SSMI.
It's SSMI.
The data is not in this data set.
It's not in this data set.
So the data set we're using is homogeneous. It's SSMI. The whole record intercalibrated.
It's the same for GPCP, I think.
AMSU data is not in GPCP. It's not in the water vapor data we're using. It's just SSMI. For the water vapor, it's SSMI over ocean. It's homogeneous. That record is actually extremely good and accurate. That's one of the really good things we have going for us.
Okay, I'd like to thank the speaker again. I'm sure if these things stay around 5 minutes, if you have any.
Okay.